Let's talk about graphing rational functions. Now remember, rational is just another word for fractional. So the functions that we're going to be graphing in this section are going to contain fractions. The numerators and the denominators are going to have x's in them. And when we're graphing rational functions, we always have to worry about asymptotes. Well, you've probably graphed things with asymptotes before, and if you don't remember, asymptotes are the dashed lines that I have plotted here. So here are some asymptotes in the dashed lines, and down here, these are two more asymptotes down here. And asymptotes are lines that our curves get really, really, really close to. They don't necessarily have to touch the asymptotes, but sometimes they do. Like down here in this horizontal asymptote, you can see the green curve touches it, crosses it, but stays very close to it. In the other blue vertical asymptotes, you can see that the curves get really close, but they don't ever touch or cross those asymptotes. So asymptotes act like magnets. They draw your curve towards them. They don't necessarily have to touch, but sometimes they do. We're going to deal with three different types of asymptotes in this section. Vertical asymptotes, like you see here, this one, and this one down here. Horizontal asymptotes, which are horizontal lines that your graph gets close to. Or in the later problems, what we call slant, or sometimes they're called oblique asymptotes, that are exactly what they sound like. They're slanty. So let me explain where these asymptotes come from. This first graph has the function y equals 3x squared minus 3x over x squared plus x minus 12. That's what our first graph looks like. And what I want you to notice about both the numerator, but more importantly the denominator, is that these factor. So if I'm factoring my denominator, x squared plus x minus 12 factors to x plus 4 and x minus 3. Now the numerator does factor. It's less important. Take out the 3x and I'm left with an x minus 1. Less important, I'm sorry, for the asymptotes. So here's what's important about the asymptotes that you see in this problem to the right. If you remember when we discussed domain for a rational function could never have x equal to 0, the denominator equal to 0. We could never have an x value in the denominator that made the denominator equal to 0. So we would say that x couldn't be equal to negative 4 or positive 3. That would make our function divide by 0. And if you look closely at the graph here, those vertical asymptotes at negative 4 and positive 3 are precisely from the values that x was not allowed to be equal to. That kind of makes sense for our graph here. We can't have any y values crossing that line, because that would imply that at x equals negative 4, we would have some y value existing, and that's not okay. It would make us divide by 0. So that is why those asymptotes, if I can make that go away, exist at x equals negative 4 and x equals positive 3. Vertical asymptotes come from the x values that make the denominator equal to 0. Vertical asymptotes come from the x values that make the denominator equal to 0. Looking at the example on the bottom, I'm going to switch to a different color pen. This one came from y equals x squared minus 3x minus 4 over x plus 2. And if you look at this one, it has also another vertical asymptote. And that vertical asymptote comes at the point x equals negative 2 because x equals -2 was a value that we could not have our curve cross. So again, that would be from where the x value makes the denominator equal to 0. This would be where our vertical asymptote would occur. Okay, horizontal asymptotes. So horizontal asymptotes require us looking at the degree of the numerator and the degree of the denominator. And you basically have two different cases. Either the degrees match, so for this first example in blue, the degree of the numerator is 2, and the degree of the denominator is also 2. So I want you to notice if you have the degree of the numerator equals the degree of the denominator, then you have a horizontal asymptote at y equals, now let's look back over here. Here's our horizontal asymptote. And if you count, this is at y equals 3. It is not a coincidence that 3x squared over x squared reduces to just 3. So actually, let me clean that up and write that in a better way. If the degree of the numerator matches the degree of the denominator, then our horizontal asymptote is at the fraction a over b, where a and b are the leading coefficients, of the numerator and the denominator. So in this case, it would be 3 over 1. Y equals 3. Another case that I don't have graphed here, where you have a horizontal asymptote, is if the degree of the numerator is smaller than the degree of the denominator. Then you have a horizontal asymptote at y equals 0. And I'll do one of those in the next example. Slant asymptotes occur in this case. If the degree of the numerator, ooh, whoops, let's spell that right. If the degree of the numerator is bigger than the degree of the denominator, so the opposite of the previous case, like in this one right here, let me erase this just a little bit. This was x plus 2. And go back to the red, x plus 2. If you look at this example, the degree, and maybe I'll highlight this, the degree of the numerator is a 2, the degree of the denominator is only a 1, so it fits. The degree of the numerator is bigger than the degree of the denominator. Now, the equation of this green dotted slant asymptote right here is y equals x minus 5. So notice it has a y-intercept of -5 and a slope up 1 and over 1. And you get that result by doing long division. You would do x plus 2 divided into x squared minus 3x minus 4. I will do that example at the very, very end of the lesson, but I wanted to show you where they come from. The numerator has a larger degree than the denominator. And when you do that long division, you get x minus 5. So like I said, we'll do some examples of those at the end, but I want to start with some simpler examples. Let's do our first example. Let's graph the rational function y equals 1 over x plus 4. So here's the steps that you should follow when you're graphing rational functions. Step 1. The first thing that you want to do when you're graphing rational functions is find and sketch your vertical asymptotes. So remember, your vertical asymptotes come from when your denominator equals 0. So in this case, that's when x plus 4 equals 0. So our vertical asymptote would be at x equals negative 4. So I'm going to draw that in. 1, 2, 3, 4. And as best I can, I'm going to draw a vertical line that goes right through x equals negative 4. Okay, second thing, we're going to find and sketch our horizontal asymptotes. Okay, now remember, when you're finding horizontal asymptotes, that's when you're looking at the degree of the numerator and the denominator. So the degree of the numerator is actually kind of difficult to see in this one. There aren't any x's in the numerator at all. And if you remember, if there aren't any x's, the degree of that would be 0. X to the 0 is 1. And that is smaller than the degree of the denominator, which happens to be 1 in this case. X to the 1 is in our denominator. So since the degree of the numerator is smaller than the degree of the denominator, then our horizontal asymptote is at y equals 0. So I think I'm going to graph that with kind of fat dashes so you can see it. Okay, and then the last thing we need to do is basically we need to just simply plot some points. So I'm going to do this in red. But I want to give myself a little bit of room so we can work here. So I'm going to erase the previous one and scooch the plotting points up just a little bit. So step number 3, plot some points. Now, the points that you want to plot are generally starting with your x and y intercepts. So for the first one, let's say we're plotting the y-intercept first. Remember, when you're finding the y-intercept, that's when x is equal to 0. So we'll take our function y equals 1 over x plus 4, and we'll plug in x equals 0. So we have y equals 1 over 0 plus 4, or y equals 1/4. So when x equals 0, y is 1/4. X is 0, y is 1/4. Okay, let's find the x-intercept. So likewise, when we find the x-intercept, this is where we set y equal to 0. Now that's a little bit harder to do in this problem. To solve, we have 0 for y equals 1 over x plus 4. And if you want to multiply both sides by the x plus 4, that's fine. What you're going to get is just that 0 equals 1, or 0 equals your numerator. Well, 0 doesn't equal 1. That's not possible. So that tells us something very, very powerful. That tells us that there is no x-intercept. That tells us that it never touches the x-axis. So our graph does not touch the x-axis. So up here where we have y equals 1/4, we know a lot of information now. We know that the graph has to get closer and closer and closer to that horizontal asymptote. We know that it can't cross the horizontal asymptote because it doesn't touch the x-axis because there was no x-intercept. We also know that the graph has to go up this way, getting closer and closer to that vertical asymptote. So there's only one other piece of information. We need to figure out what happens on this side of the graph. And the way we're going to do that is we're going to pick one more x value. something over here. Let's say x equals -6. And when we do that and plug that in, we have y equals 1 over -6 plus 4, which is y equals 1 over -2, or -1/2. So at x equals -6, y is -1/2. Let's say that's right here. Again, we have so much information from just that one dot. We know that the graph has to get closer and closer and closer to that vertical asymptote, but it's not allowed to cross it because it was a vertical asymptote from when the denominator equals 0. So like I said at the beginning of the lesson, we can never cross vertical asymptotes. Sometimes you can cross horizontal asymptotes, but not in this case because, again, it never touches the x-axis because we didn't have an x-intercept. So in order for our graph to get sucked closer to that horizontal asymptote and to not touch the x-axis, it must go up close to the negative x-axis. Okay, let's try another example. For this example, let's graph y equals 2x minus 6 divided by x plus 5. So same steps as last time. Step number 1, find and graph our vertical asymptotes. Now remember, the vertical asymptotes come from the denominator. So in this case, we have x can't be equal to -5. So x equals -5 is our vertical asymptote. 1, 2, 3, 4, 5. Oh, let me make that a little bit neater. There we go. Let's try that again. That's better. Okay, so vertical asymptotes come from the denominator. Secondly, horizontal asymptotes. These come from comparing the degree of the numerator with the degree of the denominator. So if you look at this example, the degree in the numerator is a 1, and the degree in the denominator is a 1. So the degrees match. So in this case, we have, if you want to reduce the 2x over x, just the first term in the numerator and the first term in the denominator, that's fine, but it will always be the fraction of their coefficients. So it will always be, if you want to think of these x's reducing, 2 over 1 or just 2. So I'm going to erase this and write y equals 2. And let's plot that. So y equals 1, 2. There's my horizontal asymptote. Okay, last but not least, we want to plot a bunch of points. Well, not really a bunch, as few as possible. And definitely start with your intercepts. So to find the y-intercept, again, you're going to set x equal to 0. So this will be y equals 2 times 0 minus 6 over 0 plus 5. Y equals -6/5. So I'm going to do this in red like I did in the last example. At x equals 0, y equals -6/5. Okay, let's look for the x-intercept. Remember, that's when we set y equal to 0. So if we set 0 equals 2x minus 6 over x plus 5, if you want to think of it as multiplying both sides by x plus 5, that's fine. What you're always going to get is 0 equals the numerator. So a lot of people skip to this step when they're looking for the y equals 0 portion, when they're looking for the x-intercept. Now this one actually does have an x in it we can solve for. So when we add 6 to both sides and divide by 2, we get x equals 3 as our y-intercept. So 1, 2, 3. So now that's actually really, really helpful. Not only does it give us a point, but remember, this is the only place that we can have an x-intercept. We didn't get 3 and -7. We just got one value. So here's all the information that those two little dots tell us. They tell us that this graph must behave like that. We have to get sucked towards those magnets, towards those asymptotes. We're never allowed to cross a vertical asymptote because it comes from when the denominator equals 0, and that's not okay. However, sometimes we can cross the horizontal asymptotes. So we know our graph goes up towards that horizontal asymptote, and we know it passes through x equals 3 and y equals 0. I'm going to come back to crossing the horizontal asymptote in just 1 second, but here's what I want to point out. On the other side over here, we actually do know what our graph looks like on the left-hand side of the graph, even though we haven't plotted any points like -6 or -7. So pay attention to this. The graph due to the asymptotes either has to look like this or like this. Now, it can't look like both because that would fail the vertical line test and not be a function. However, the graph cannot look like this, and that's because there would be another x-intercept over here that we never found. We only found one, x equals 3. So because we only have one x-intercept, x equals 3, this is not possible. So I'm going to erase that. That's not possible. And I know now that the graph must be up here. So if you want to, you're welcome to plot, maybe find x equals -6 or x equals -7, and you should, barring any arithmetic mistakes, get ordered pairs that are up here above your asymptote. Okay, back to the horizontal asymptote. If you want to see if your graph crosses the horizontal asymptote, remember that that horizontal asymptote was at y equals 2. So if you want to see if your graph crosses y equals 2, your horizontal asymptote, do the same kind of thing we did when we set y equal to 0 over here. So if we're checking that, take the y value, set it equal to 2, 2x minus 6, x plus over x plus 5. Multiply both sides by the x plus 5, so we have 2x plus 10 equals 2x minus 6. And we quickly run into a problem. If we try to get x by itself by subtracting 2x from both sides, we get 10 equals -6, which is not possible. So if we have something that is not possible when we're looking for the y equals 2, the horizontal asymptote, we can tell that it does not cross. And now we have a pretty decent picture of what our graph looks like.